So we'll have a look up here. We'll go through it, and you're welcome to copy down as I am doing it, but make sure you follow, at least paying attention here. So I've drawn up triangle A, B, C, D, E, okay? And B is the midpoint. We know that because AB is equal to BC, and E is the midpoint of AD because AE equals ED. That's the information that we're starting with, okay? And what we're trying to do is we're trying to prove that BE is going to be parallel to CD and half of its length. That's what we're set out to prove here. So what we're going to do, we're going to start with what we can call a construction. Okay, so this is why it's challenging. And a construction is where we insert more lines into it. We either insert more lines or points or something like that. And so I'm going to construct this new line going out in this direction. And we can do that. And I'm going to make it parallel to this line AB. Okay, so that this and this line are parallel. Okay, so whatever the angle is there, we're going to have the same angle there. All right, they're going to extend in the same direction. All right, they're parallel. That's what we're dictating. And then I'm going to draw the line through here. We're going to have BE, and it's going to meet here at F. Okay, so we've just constructed there. We've got this line and this line are parallel. These sides are equal. And then we're ready to set about our proof, okay, because we're going to use this figure here to come up with our proof. So the first thing we're going to do is establish that ABE and EFD are similar triangles, okay? So we can see that these angles are equal because they're vertically opposite. So that's going to be the first statement that we make. Angle BEA is equal to angle DEF. All right, that these angles in here, because they're vertically opposite. Okay, now we established, by dictate, that these are parallel, okay, which means this angle and this angle are alternate angles in parallel lines. That angle EAB is equal to angle EDF. And I'm just going to put up here, let's call that alpha, let's call that beta. Now what we can see here, right, is that we can even prove that these triangles are congruent because this side is the same as this side. So we've got AE equals EB. And we have enough information to prove these triangles are congruent because they have two angles that are the same and a corresponding side in the same relative position. Okay, it connects A and B here and it connects A and B here. It doesn't matter what its length is. We don't know what its length is. That doesn't matter, but they're the same size because point E is the midpoint. ED, thank you. Yeah, got my angle beta there. Thank you, Maddie. AE equals ED. That's given to us. And so therefore, triangle ABE is congruent with triangle DEF. That this triangle here and this triangle here, they're the same size and they have the same internal angles. Okay, so then what that means, okay, we know this length here and we go, well, that means it's going to be the same on this triangle over here. AB corresponds with DF. Okay, so therefore, AB equals DF because it's a congruent triangle. And so we can put a line there. Okay, and we're off to the hills now. We're away. That's a B. Now we have CBDF is what shape? It's a parallelogram. We have parallel lines here. We know they're parallel because they're going in the same direction, and they have the same length. Okay, which means these two lines, BF and CD, are parallel and the same length as well. Okay, so therefore, BD is parallel to CF and BD equals CF. BF and CD. Okay, BF parallel to CD, BF equal in size to CD. All right. Now, so we've established that these are parallel. Okay, so that's the first part of the midpoint, is that these two lines are going to be parallel. If that line's parallel to that one, this line being just a mitigated version of this line, it's going to be shorter, it's going to be parallel as well. They're in the same direction. So we've established that it's parallel. That's the first part of the midpoint theorem. The second part is we need to establish that BE is half the length of CD. Well, BE, we know BE is equal to EF. All right, and we know that because these are congruent triangles. These two are congruent triangles, which means their corresponding sides are equal. We established AB is DF. We established AE is EB, so that means BE is EF. They're equal. And so that means BF, the length BF, is really equal to 2 times length BE. And we know as well that BF is actually equal to length CD. That this length here and this length here are equal. So that means CD is equal to 2 times BE. Okay, so this is probably one of our most complex proofs. All right, so let's just talk through it really quickly. What have we done? We did a construction. We drew that line there, and we established that this triangle and this triangle are congruent. They had two internal angles that are the same. We can even demonstrate that all three are the same, but that's not necessary. Two that are the same, and we had one corresponding side that was the same. That means they're congruent. Because they're congruent, this side and this side are equal to one another, which means this is a parallelogram, which means BF and CD are equal. It means they're parallel. And then we said, and we know this side and this side are equal, so that this is the midpoint of this line. And so BE, or 2 times BE, is equal to CD. That's the algebra we processed over there. So that's the proof there. Might go through it again tomorrow. We'll see. Let's talk about the converse to it, which is a fair bit easier. Okay, so what did we prove? Proved that the midpoints, the line connecting the two midpoints, is parallel to the third line and half of its length. That's what we've proved there. They're the two properties we've proved. So now let's look at the converse to it. So we've got converse to the midpoint. We're going to start with the same sort of diagram, but from memory, we don't need to go the whole way. We don't need the whole construction. And the only thing we're dictating is that these lines are parallel and that these are equal. That's what we're starting with. Okay? We don't even need to know the length of the other side. Now, we're going to establish that triangle ABE is similar to triangle ACD. You can see it by looking at it, okay? But we need to demonstrate it. We need to prove it using our notation. So firstly, triangle BAE, angle BAE is common. Okay, it's common to this triangle and it's common to this triangle. It's a shared angle. It's in both of those triangles. So we have one angle that's the same. These lines are parallel, which means these angles are the same. because they're in the same corresponding position, and these angles are the same as well because they're in the same corresponding position on a straight line. So we've got angle BAE is common, and we'll have angle ABC. I'll just rub that out so we're not getting confused. Angle ABE, sorry, is equal to angle ACD, and they're corresponding. So therefore they're similar. Okay, they've got two angles out of the same, therefore they're similar. And I might draw them both separately. I'm just going to isolate them just for the purposes of our proof, just so we can see pretty clearly what's happening. So if we define this length as x, okay, that means this length here is going to be 2x because it's twice as far. Length AC is twice as far as AB. Okay, and then we've got these points over here. We've got this side is going to be AE, and this side is going to be AD. All right, so on the little triangle, it's AE. On the big triangle, it's AD. And then we're just going to demonstrate 2x divided by x. Okay, we've established they're similar. So that means we can apply the rules for similar triangles. Watch here, Seb, Noah. 2x divided by x is equal to AD divided by AE. Okay, the x can cancel here. So we've got 2 equals AD on AE. Or we can multiply both sides by AE. 2AE equals AD. So that one a fair bit easier, no construction involved. We just establish that they're similar triangles. Because they're similar, their sides are in a similar ratio, and therefore 2 lengths of AE is equal to AD. So that means BE bisects AD. What have we proved here? Here we've proved that this line, the line that's from this midpoint, that's parallel to this one, bisects this line. Okay, so it's the converse to the midpoint theorem. Here we started with the 2 midpoints and a line drawn through them, and we proved that it's parallel and half its length. So it's the same rule, but we can apply them in different ways. Okay, all right, yep. Excellent. So that's the proof there. Let's proceed with similar triangles.